The City of Logan owns and operates wastewater treatment plant, which is Lagoon Systems. These lagoons receive approximately 14 million gallons a day from 7 cities in Cache County. We've been asked to reduce the phosphorus content of the wastewater we release to the Cutler Reservoir. Our approach to wastewater treatment system is we want the system to be sustainable and cost-effective. Our goal is to work with USU and the SWIBEC Center to come up new technologies that will allow us to run a very sustainable wastewater treatment system that will help the environment reduce cost. And we hope that these technologies will be demonstrated and used in this system, and other communities may be able to benefit from the new technologies generated right here in Logan.
Algal-based biofuels team at Utah State University has had a lot of success in growing algae and understanding the criteria for growing and harvesting algae in a laboratory environment. Now we're ready to take the next step, and that's to go to large raceways where the concept is having a design that could be replicated over thousands of acres so that you can grow sufficient algae to produce bio-oil that could have an impact on our energy production system.
The purpose of those algal ponds is to grow as much biomass as possible. What happens when the algae starts growing up, it starts to grow up in such a high density, high culture, that it starts shading the sunlight from other algal cells. The paddle wheel mixes that culture and exposes that algae to as much sunlight as possible. It helps the culture from settling out. So in these ponds, we want to grow up that algae as high as possible.
This facility here represents a major step forward in allowing us to study the step-up procedures that allow us to increase the productivity or the yield of algal biomass and lipids that can be converted into oil.
In certain situations, under certain conditions, algae will grow as a biofilm, so a sticky slime that's attached to a surface. And what I did was learn about materials that the algae will stick to and grow as a biofilm, and I designed a rotating algal biofilm reactor. And that's what these are behind me here. These reactors are submerged in the wastewater partway, and as they rotate, you treat the water, get the nutrients from the water, and then also the algae in the biofilm, when they're up, can take CO2 and also get the sunlight that they need to grow. And the beneficial part of this design is when it comes time to harvest, because it's already a thick biofilm slime, you take the rope that the biofilm is growing on and unthread it, unspool it, scrape off the biofilm. There's your biomass, your algae, and then you can reload the reactor, rewind the rope on, and start again. Continue treating the wastewater and growing more algae to be used for energy production while the water is being treated as well.
One method that I'm looking at is this device called a dissolved air flotation unit, also known as a DAF, a DAF unit. It works on a couple of just really simple principles. We have our wastewater flow into 2 large mixing tanks where we can add in some low amounts of chemicals. That starts this process of bringing the algae cells together so they don't repel each other. After we have 15 or 20 minutes of a mixing time, that pumps into what we call our flotation tank. While the mixing is going on, we have some of this wastewater is pressurized with air, and then when that re-enters the flotation tank, we have lots of bubbles, and those bubbles are able to lift up our algae. By this point, is already formed larger clumps that we call flocks. Those are then able to raise to the surface and collect on the top. And then we have a scraper that runs on like a conveyor belt system that we're able to just scrape the algae off the top of the flotation tank. I'm also running a small scale, what we call a benchtop unit, which mimics the DAF operation. And on that unit, I have 6 1-liter jars. where I can vary very easily different chemical dosing, different recycle rates. I can vary different parameters of a DAF and do it all very quickly with different jars. And allows me just to run it quick, clean it out, run it again. I can run that, 3 or 4 or 5 times a day. So I'm trying to optimize it and do a more natural and a more efficient way of getting our algae out of the wastewater.
The algae, when they're growing, they'll take the sunlight and they'll take the carbon from CO2, and under the right conditions, they'll store that in the form of lipids. So what we do is then harvest the algae at the optimal point in time and extract those lipids and use them as a feedstock for a biodiesel product. We take algae, extract the oil from algae, and have this direct drop-in replacement fuel that can then go out onto our existing fuel infrastructure. America has this insatiable appetite for liquid transportation fuels. A long time down, in the future, we might be able to just use electric vehicles on an electric grid or with batteries. But for now, we need liquid fuels. And biodiesel from algae is a very promising solution to that issue.
We use algae biomass to generate biogas, industrial solvents, and bioplastics. So the biogas is basically produced using a series of microbial anaerobic processes where certain microorganisms break down the algae biomass that can then be used by the methanogens, which actually generate methane gas, to then produce the biogas, which can then be used subsequently to run generators, steam turbine generators, to generate electricity. We can also generate industrial solvents. So we use anaerobic microbes basically that can degrade the algae biomass to generate these solvents. And we're doing this currently at a laboratory scale, but the idea is to optimize this degradation of algae biomass to industrial solvents. And once that's achieved, we'll move to pilot scale and then industrial scale to produce these solvents. So in addition, we're also trying to screen different algae that are present in the wastewater treatment facility that produce different types of biopolymers which can be converted into bioplastics. And these bioplastics can replace essentially all the plastics that are used throughout, for example, shampoo bottles, water bottles, etc. You name it, we can replace those plastics with bioplastics, which are naturally degradable and substantially better for the environment.
Every community in the United States has the key resource for this type of industry, and that is wastewater. The challenges in this industry are to develop and scale up those new technologies that provide cost-effective solutions, not just for wastewater remediation, but go beyond that so that we can develop bio-based industries and bioproducts to convert chemicals in wastewater to bio-based industries. SWEBEC is dedicated to meeting these challenges.